Everyone, my name is Sid Iju. I'm from the Denver Metro Regional Science and Engineering Fair, and today I'd like to show you my project for Stay Home in Science, which was about predicting the onset of Alzheimer's disease using graph neural networks and diffusion tensor imaging. So the problem I set out to solve involves Alzheimer's disease. Alzheimer's disease is an irreversible progressive brain disorder that slowly destroys memory and thinking skills and is the most common cause of dementia among older adults. And due to the complex pathology of the disease and the late onset of clinical symptoms, it's difficult for researchers to adequately detect and treat Alzheimer's effectively. So the research question I set out to solve accordingly was, is it possible to accurately predict the future onset of Alzheimer's disease using diffusion tensor imaging and graph neural networks? Because for diseases such as Alzheimer's, time is critical, and so finding a way to detect Alzheimer's earlier would enable doctors to begin treatment for Alzheimer's earlier and thus slow down the progress of the disease and improve quality of life for its victims. And now for the theoretical background for my project. The first component in this section is diffusion tensor imaging. Diffusion tensor imaging is a type of MRI that tracks the path of water molecules in the brain. In my project, I acquired DTI data from online datasets and resources and used various tools and scripts to convert each DTI image into a tractography analysis. And then for use in the neural network, I then convert each tractography analysis image into a connectivity matrix, which is a matrix that shows the strength of connections of different regions of the brain. The second component of my project was the graph neural network. Graph neural networks are an abstraction of regular neural networks that allow for training on relative spatial data such as the connection of different regions of the brain. They differ from convolutional neural networks in that the idea of a convolution is not strictly defined in a graph neural network. In regular neural networks, the transformation of an image, otherwise known as a convolution, is strictly defined as a pixel-wise transformation where each pixel is transformed in accordance to its neighbors and their properties. But in graph neural networks, this is different, as I will soon explain. Because in graph neural networks, you can sort of experiment with different convolution filters that sort of change the idea of the convolution. There were various types of convolution filters I experimented with in the creation of the graph neural network. The first one is called the aggregate filter, and it basically performs the same function as a typical convolution does. It sums the neighbors of a particular node in a graph and uses that as its transformation. The spectral filter, which was the final filter I used in my graph neural network, transforms the original graph by a clustering operation. It uses the eigenvalues of the Laplacian matrix for a graph to determine how connected different regions of the graph are and then cluster nodes accordingly. I use the spectral filter because I guess that regions in the brain that are closer to one another would have more related functions and so facilitate the use of a spectral filter. And that's showed in my results because to evaluate the success of my model, I compared it to a previous convolutional neural network baseline across a variety of metrics. And over the metrics I used, such as accuracy F1 score, which is a measure of the precision of a neural network, and RC-AUC, my network outperformed the original baseline. And in particular, it improved by around 5% in accuracy and around 9% in RC-AUC. And so overall, the graph neural network I created showed significant improvement over the baseline convolutional neural network. And the contributions of my project are that I showed the viability of a graph neural network approach on spaces where traditionally convolutional neural networks are dominant. In addition, regarding the focus of this project in particular, my neural network has the capability to improve how doctors respond and deal with Alzheimer's disease. There were some limitations in my project, the two main ones being data and storage. So because due to the relative sparsity of diffusion tensor data available online, I had a very limited data set to work with. And this in turn likely affected the performance of the model. And I believe that with more data, my model will be able to improve even beyond where it already is. In addition, limitations in the storage I had to work with affected how deep I could make my graph neural network model, and perhaps with more storage I could train my graph neural network model with more layers, although I am unsure of whether this would improve the model's performance. And now for some future paths I'd like to look into. First, I would like to experiment with some different choices for the regions in the brain I chose to analyze in the tractography analysis stage. Although I used regions of the brain known to be related to Alzheimer's, I could test whether other regions might in fact have more to do with Alzheimer's than it seems. I could also experiment with other convolutional filters for the graph neural network, such as Chebyshev filters and Fourier filters. And finally, I could also try out my algorithm on other datasets to ensure its performance is not due to some irregularities in the dataset I used. And that is my Stay Home in Science project. I really hope you all enjoyed, and please make sure to take care and stay healthy. Thank you.